Welcome to a live simulation of a semiconductor production line. Two production orders wait on the left. They run on two different technology routes, yet they share the same physical stations. Let's start the line. Order 118 splits into two batches that travel onto the line. Before every station, a batch first sits through a standard queue time. Then the machine takes it, one batch at a time. Note the amber station. On CVD, this route's bottleneck. Its cycle time sets the rhythm for everything downstream. At hour 24, order 121 is released. Its route is shorter, 6 steps, skipping wafer-level fill and assembly, and its bottleneck is different, BEOL metal. Two different products, one shared factory. This is where scheduling gets interesting. Here comes the first collision. Batch C. One needs only 20 hours on ON, but the station is busy with the other order's batches, so it has no choice but to wait in line. Cross-order contention like this is invisible on paper, and it is exactly what naive plans miss. Now let's make things worse. The bottleneck itself just broke down. On CVD goes dark for 12 hours. The batch inside is frozen mid-process, and everyone behind it stalls. In planning terms, this is a blackout constraint, capacity that simply vanishes from the calendar. A VIP customer calls, a priority one hot lot drops onto the line. Watch it cut straight to the front of every queue. Priority doesn't create capacity. It only decides who gets the next free slot. Someone else's batch quietly pays the price. Time to fight back. We bring a reserve tool online at the bottleneck. ON now runs two batches in parallel, and the backlog drains twice as fast. That is the tools up factor of the effective capacity formula, finally working in our favor. Now a crucial contrast. This time I break a fast station. HERC etch, not the bottleneck. Watch closely. The batch inside pauses, yet the line barely reacts. Because HERC runs faster than the bottleneck can feed it, that spare capacity quietly absorbs the shock. Break the bottleneck and everything freezes. Break a station with slack, and almost nothing happens. That asymmetry is the very heart of scheduling. This reveals the iron law of the line. Throughput can never beat the bottleneck's rate. You can tune every other station to perfection, but until you widen ON, the whole factory still ships at ON's pace. That is exactly why we added the reserve tool there and nowhere else. Find the bottleneck, and you find the only lever that matters. Let the line run. Watch the red particles. Every station scraps a slice of each batch, and probe, at 93% yield, always reigns the hardest. Below each station, the utilization strip tells the real story. Bottlenecks glow in long stretches, while CMP barely flickers. Let's read the scoreboard on the right. Work in progress counts the batches live on the line. Total wait hours reveal where time is being lost. Wafers out shows the real yield after every station has taken its cut. And lead time, from release to shipment, is what the customer actually feels. Every move trades one of these against another. Balancing them is the optimizer's whole job. One more principle, leveling. A good schedule doesn't just run fast. It spreads the load so no tool group spikes on any single day. Smooth those peaks, and you cut queues, overtime, and risk all at once, without buying a single extra machine. One last experiment. The same demand, but every lot split in half. 8 small batches instead of 4. The line pipelines beautifully, and the first wafers ship far earlier. The cost? More moves and more queues. Every scheduling choice is a trade-off. And that is the whole scheduling problem. Capacity per tool group, per day. Bottlenecks that set the rhythm. Breakdowns, priorities, and trade-offs. A human can watch one line. A production scheduling optimizer weighs millions of these decisions at once, across every order, tool, and day.